อยู่ในห้องนี่แหละแต่ผมจะประชุมไปด้วยแล้วผมจะเปิดวิดีโอนะครับ so we're gonna start our lab today and our lab that we have to do experiments is called timers. I still remember about timers in my professor class. That is a lot pieces that we learned from the class. Anybody remember? No one. Why? By the way, what is timer? Timer is like a clock. There are some clocks inside our CPU that related to real times. So what does it mean by real time? It's not the time that you can measure. Because before this class, when you did this create the delay functions, you don't have any clue how long does it take, right? You just randomly select some number and put it to that functions, and maybe it generates sometimes delay, but you don't know exactly what the time that function generates. But in today's class, we will do some experiments on timers. Therefore, if timer is related to the real time, so what does it mean? It means that when you use it, you can create any kind of times. Okay, so what is the time that we want? It depends on the applications, and today we will see at least 2 applications. The first one is the time itself. You will use timer to create a delay function, very precise delay functions. So if you want this delay to have like a 1 milliseconds, you can use timer to generate 1 milliseconds. And you use oscilloscope to capture and see that delay in real time. And the other thing is that you use the timers, because the timer is like a clock, so it's counting up or counting down, right? And counting depends on the frequencies of your CPUs. Therefore, in this case, we will use the property of countings in our timer to be counters, and to use the other tools, the other device that useful for our electrical engineering. Go to the factories. It's gonna be something like this. Okay. So what is it? It's called encoder. So in this one, you can measure the angle of everything on, and I will explain it later after we go through that part. Okay, let me change to this one. Is much more better. Okay. So basically, you use the clock from your oscilloscope pass through maybe PLL to boot up into the certain frequencies. For example, these examples, okay, we will boot up our crystals from 8 MHz to 14 MHz. Then we use it as an input clock to our module. Then we can do some T-scaler. We can have some device that sometimes we don't want to use that very high frequencies. Then we will get something called a timer clock that you feed to your timer systems. So please change this equation a little bit. In here, we should have F timer equal to F clock divided by SPC plus 1. So what is a SPC plus 1? SPC is pre-scalars. So by using these equations, you will find out if you want to divide your frequency by 20s, you have to set PSC equal to 19 in order to 19 plus 1 equal to 20s. Okay. Why we have to have a plus 1 here? It's because sometimes if you just ignore to do anything about the prescaler, the value can be zeros, and if you divide something by 0, you're gonna get some hard error. So that's why they just add 1 to make sure that you did everything correct here. Then the timer clock in this case, 2 MHz go to the timer or counter circuit inside your CPUs. Then they will get a lot of things that happen here. They will count the value up, right? And if your value is greater than some things, they will change the output. So in that mode, we call the output captures. And also you can make this timer to be auto reload timers. So what does it mean? It means that when you count to some certain values, then it will reset back to the original value. Therefore, by using this one, you can control the time because you know exactly how much time or how long does it take because you know the frequencies of the input. Then you know exactly how much that have to count, and you can reload it to make things start from the beginnings. By using this one, we can start the first experiment. It's a timer module, and we will use output capture. Output compare or OC mode. And for the input captures, I will explain you when we go through that part. Okay. The first experiment, what we try to do is we try to start to use your timers. In this one, you will create the project, name that file, then you write down the code, the functions called timer pre-delay into the main programs. Okay, in this one, you will start your timers with certain amount of numbers that you want to count, then you wait until it finishes, then you disable your timers. Therefore, by using this one, you can control a time. Then these timers will generate exact value delay for you. Okay. Then we have to write down our GPO functions, otherwise we cannot use anything, right? Then we will have the other functions called timer tree set up. In this case, we will use timer trees as our target timer today. Basically, we have a lot of timers in our systems, okay? But most of them we can use like this because we will use just like a general purpose timers. Therefore, you can use timer 1, timer 2, timer 3, timer 4 as the regular timers. Then this is how we set up. Okay. In this case, because of our timers using the frequency of our CPUs is 22 MHz, then you can use these calculations to find the frequencies of your timer. In this case, it's equal to 1 MHz. So what does it mean? In every time this count is 1 microseconds. And if you want to count 50,000 times, it means you can generate 50 milliseconds out of your timers. Then to set it up, you just set the prescalers as I show here. Prescaler is 71. 71 is converted into hexadecimal 0x47. And we will use the timer mode count up. Then we will select the period. So how long does it take before it's rolled back to originals? In this case, we set to 49,999 value here because if you want to count up 50,000 times, we have to set this number minus 1. So it should be here. And finally, we just set it into our timers. And after we start our timer, the timers will generate 50 milliseconds for us every time. So what is it that happens in the main program? In the main program, it's just nothing. We just create the functions that create this code, and we just do some GPIO configurations and also the timer setup. Then you have the state here that. Okay, can you change the code a little bit? Can you change the code here? State equal to 1 is to 0. Here. Then basically this one will blink your LED onboard using the timer tree delay. And after this, after you finish this one, you just compile it and download to the board. Then you will use oscilloscope to see what is the real LED frequencies. Is it 50 milliseconds or what else do you have here? Okay, and after that you have to answer that how to generate 1 second delay using the code in the experiments, and after that you can get the signatures. Okay, and for the second experiment, we will focus deeper into the modules. In this case, we will be talking about something called public modulations or PWM. As you know that the PWM is the ways that we increase the numbers or information into our digital signal, right? Because digital signal, not like analog signal, that the amplitude have meanings. But in this case, we have to change into the duty cycles in order to increase the information that embed in our signals. In this case, we use that signal and we try to generate it. It's using something called power width modulations. And in this case, power width modulations of PWM can be represented in duty cycles. So what is a duty cycle? The duty cycle is the on time divided by the periods. So it's on time plus off times. And you can see the way like this. You have 2 units of time here for logic 1, and you have 4 digits here, 4 units here for logic 0. Then the duty cycle will be 2 divided by 6. So this is the duty cycles of your signals. Okay. And if you combine 1, 2, 3, 4, 5, 6 here with the real units, then you will find the frequencies of the PWM signals. And luckily, because of our timers can generate PWM signal for you directly, how can we do it? We will use extra configuration here. In this case, we will use output compare TMX-CR registers to make a comparisons between the numbers that count inside your timers with the value inside these registers. And if the values inside this register is still greater than the value in your timer, then it will produce logic 1. But if your timer's values is greater than this one already, then your logic will change from 1 to 0. By using this one, you can control the periods of your PWM using the auto reload or ARR in this timer. But you can control the duty cycle using output compare register or TIMX CCR. Okay. And I will, in this case, to make your life easier, then is the PWM signals that output from the comparisons will connect to LED9 here. Then you will see LED9 on your board that show something called PWMs. Then when you change the duty cycles, then the brightness of the LED will change. And that's what we try to do in these experiments. Okay, in this one, you have the same projects as experiment 5.1. You have to add the MC ABC init read ABC1 for experiment 3 to your main programs. Then you change your code in Hammer 3 setup as this follows. Because right now we require 2 things. The first thing is the periods that you can set to your timers registers. And the other thing is the duty cycles of your PWM signal that you have to set into your output compare registers. Okay, so by setting up like this, then you can generate PWM. And for the PWM set, this is the functions that you use to set the duty cycles of your signals. You use these functions. Then for the main program, you do nothing. You just read the values from ABC1 on your board. Okay, then that LED will reflect as the duty cycles on your LED. Then what does it mean in that? When you turn your variable resistor here on your board, then the LED brightness will change. Okay, you will see it in action later when you go to this part of the code. Then you have to answer the questions, and you have to answer this question also. That's why you need to set timer based in the structures of this scalar to 0x 5f. Okay, then you will get the signatures. And the next one is called incremental encoder reader. So what is it? Okay, this one is involved with the job that you may be have to do in the future when you go to the factories. You will have to read some value from your motors or maybe the conveyors belt. Then this is the sensors that we can measure the angle of things. It's called encoders. So what actually is it? This is a light encoders. So when the shaft here is rotated, it generates a pulse. And the pulse that generates, we have two phases. It's called phase A and phase B. And you can see here, the phase A and phase B will shift with 90 degrees from each other. And by using the patterns that you can see here in clockwise and counterclockwise directions, you can see how much the shaft rotates. And because of there are some specifics in this one that you will have 300 power per revolute. So what does it mean? When you rotate this shaft one turns, it generates 300 pulse out of it. So it generates phase A pulse 300 and phase B pulse 300, and combine them together with these patterns, then you can capture which directions that the shaft is rotated. And if you can count the numbers, then you divide by 300 and multiply by 360, you know exactly what is the angles that this shaft rotates, right? So in this case, we will use this sensor or encoders in order to see the behavior of the rotations, and we can capture it. And in order to capture it, because this one is very popular in the factories, therefore they have this module already inside our timers. It's called encoders reader. So sometimes it's referred to input captures. Okay, you require two input pairs. It's called T1 and T0s that will connect to phase A and phase B of this encoder. Then by using counters, we can count up or count down. It depends on patterns that have appeared on your T1 and T2 pairs that connect to phase A and phase B. Because if you rotate clockwise or counterclockwise, the pattern is different. Okay, you can generate something like this, and finally you can capture how many turns that your shaft is rotated. Okay, but how can you connect these sensors to your board? And you can take a look into your board. You will see one terminal or one header is showing here. Okay, and in this one you have, if you just take a look into your PCBs, you will see ground, A, B, and +5. Okay, you know from this one, it's gonna be something look like this. It's a ground, A, B, and +5 volt. And why this one is very important? Because if you just take a look into your encoders, they will say like this. For the brown line, you have to connect to 5 volt. For the blue line, you connect to 0 volt. For the white Y is output B, and for the black is output A. So the color reflects the line here that you have to connect from output A to A, output B to B, 5 volt to 5 volt, and ground to ground. Then by take a look here and also take a look into your PCB here, finally you can connect it to the board. And be careful when you connect, make sure everything is correct before you start to use it. Otherwise you can burn this one. This one is very easy to burn, and it's about 700 baht per each one. Okay, so be careful before you use it also on the board. Then we can start our experiments. In this one, you just add the functions USR sense, USR setup, USR put S from the experiment to into your main programs. Right now your main program is very big. Then you add this code, and it's called the timer encoder setup and encoder update. So basically just follow this one, then you follow this one, and finally you will get the value from your encoders and you just send it into your serial communication to show you how many turns that you made or how much the encoder moves in the raw format. Okay. And after that, you have to explain more about what happened here. And as you can see, I show you that the value that your board you send to your PC is a raw value. So you have to find a way to convert that one into the real angles. I already mentioned to you already. So you have to write it down and change it into your code and to get the signature here. Okay, so that's it for today's experiments. Okay, so okay, that's it. And for the homework, it's just nothing. It's just give you to work on some PWM signals that you have to generate 100 Hz, and these cycles can be controlled by using variables resistors. Okay, and these cycles have to change between 1 millisecond as minimum to 2 millisecond as maximum. Okay, why this experiment, this homework come out on this experiment? Because if you just take a look here, 1 millisecond and 2 millisecond is related to specific motors that you can use in the future. It's called servo motors. So basically, this one is used to have some experiment with the servo motors. But anyway, we can check the output using oscilloscope. Don't worry about that. Okay, for today lab, you have to have this board. Also, please take one of these encoders to your tables, okay? And don't burn it, okay? It's very expensive one. And if you're ready, you can start your lab right away. Thank you.